This lecture is about universal motors. We will talk more about their operation, characteristics, torque, speed, advantages, and disadvantages. So let's get started. So the universal motor is a type of motor that consists of field and armature connected together, whereas certain motors like induction motors are not electrically connected to each other. The rotating part and the fixed part, that is the stator and the rotor of universal motors, are electrically connected to each other through brushes. So essentially, the universal motor is a variation of the DC series motor. This can be seen in the way it is connected. So we can have a representation of the motor as below. So this represents the construction and the connection of universal motors, whereby the round circles represent windings or connections that you make in either the stator or the rotor, that is the field or the armature. So in this case, you have field windings on the fixed part of the motor, and the flexible, or rather the rotating part of the motor, has armature windings. Now the armature windings are connected to the field windings through brushes, which are usually made of carbon, and they connect in between. They are physically connected, electrically connected between the two. So what you ultimately have is an electrical flow or a current flow from one part of the winding in the field across the field winding itself, through to the armature, and through the armature itself, out of the armature into the field winding, and once again completing the circuit. So in this particular case, because of the way the windings are connected, you have a configuration that enables fields to be set up within the motor itself. So for the sake of illustration, let us say that the current flow is in the direction given, whereby at the bottom part of this winding, the current is flowing into the winding, and at the top part, it is appearing to flow out of the screen. Likewise, on the other side, we have the current appearing to flow into the windings and out of the windings at the top. So you would be able to note that because there's a current flowing through the field windings, they will have a magnetic field set up within them. And this is dictated by the action within. So if you have current flowing into the windings in this part of the field, it will generate a clockwise motion in the magnetic field, so a clockwise direction. Likewise, at the top, you have a magnetic field that will have an anti-clockwise direction. Similarly, on this side, you have the same thing, a magnetic field that goes that way, and here you have a magnetic field that goes in that direction. So what this ends up becoming is, you will have in this particular configuration a north pole and a south pole, and a resultant magnetic field that moves in that direction. So you have a field winding that is setting up a magnetic field through the armature, and the armature has currents flowing through it. Now the currents flowing through the armature are in this particular configuration, whereby you have those moving, the currents moving through that way. Now, when you have a magnetic field in a current, across a current carrying conductor, there is a torque that is acting on the current carrying conductor. So in order for us to understand the direction of the torque that will take place, we make use of the left hand rule. So the left hand rule represents the various components or the various phenomena within this setup. So the first finger in the left hand rule represents the magnetic field. The second finger represents the direction of current flowing through the conductors. And the thumb, which are all at right angles to each other, is the ultimate motion or torque that will act on the conductors themselves. So by looking at it from that point of view, you will end up having on the left hand side, because the current is going into the screen, it appears to go into the screen in this direction. We point our second fingers into the screen, and the magnetic field is moving towards the left. So your first finger is pointing towards the left. Your thumb will be pointing in a downward direction. And on the opposite side, because you have the current flowing in an opposite direction, the motion will be in that direction, upwards in this particular case. So here you can see, simply by setting up a magnetic, or rather an electrical current across the machine itself or through the machine itself, you end up with a torque that will tend to move the conductors around. Now, in the case of the DC series motor, you will only have one direction of current. However, here we are talking about a universal motor to which we will apply an AC voltage. Now, the AC voltage, of course, tends to change direction several times per second, and we have cycles of direction change. So let's see what happens, retaining the same configuration. What happens if you change the direction of flow of current? So here we have the current flowing in an opposite direction, where you have it going in the opposite direction from what we had before. And therefore we have the opposite currents being shown within each of the windings. So where current was flowing into the screen, it flows out, and where it was flowing out, it flows in. So in this case, you will notice that the fields, of course, will be in opposite directions to what we had before. So this becomes a south pole because the magnetic fields have reversed, and this becomes a north pole because the magnetic fields have reversed as well. Okay. Now, what happens in this case to the armature? The armature, using the same left-hand rule, now has the action of the magnetic field in the opposite direction. So our first fingers are pointing in the opposite direction. However, if you look at the left-hand side, the direction of current is actually out of the screen. It is pointing outwards, and our fingers are pointing to the left. Our first fingers are pointing to the left, and our second finger or middle fingers are pointing towards ourselves, out of the screen. That means that the thumb or the motion remains in the same direction that we had before. Okay, so the motion remains in the same direction that we had before, whether or not you change the AC itself. So this means that whether there's a direction change of current or it is DC being used, the universal motor will remain in the same direction. The motion of the universal motor will be still in the same direction as before. And this is a property that allows it to be used both with DC and with AC voltages. So let's look at the equivalent circuit of the universal motor. The equivalent circuit. We have a field winding, which is represented in a similar way to what we have had before, which is you have a resistor representing the real components, and you have an inductor or a reactance representing the imaginary or reactive components. On the armature side, we have a resistance, a reactance, and an equivalent voltage. And this is all supplied from our single phase AC voltage, and you have one current flowing through the entire machine as we had seen before. It is a common circuit all the way through from start to finish. So it can be represented as we are seeing there. So now let's talk about the torque speed characteristic of the universal motor. You will have an initial torque which is very, very high, and it will get lower as the speed tends to be reached. So you have that kind of characteristic of the relationship between the torque at the beginning or at zero speed and the torque at full speed. So what tends to happen is that this is advantageous for applications where you have a need for initial torque that is very high. So it is able to start when it is on load. And the advantage of that also is it can also be used in portable equipment. Because it is a compact design, you tend to have, it is very common in applications where you don't need much torque. So the advantages are it has a high starting torque, and it is usable for portable equipment. So what are the disadvantages of the universal motor? The main one is due to wear and tear. Now, in the case of induction motors, there is no physical connection between the winding, or rather the field and the armature, or the stator and the rotor, the moving part and the fixed part. The only moving part is the rotor itself, which is mounted on bearings. Now, in this particular case with universal motors, you have an electrical connection. Because you need an electrical connection between the field and the armature, this point of connection, which is indicated here, these 2 points of connection represent the weak points in the design of the motor. At this point, you have physical brushes, usually made of carbon, which connect the electrical current from the field to the armature. So these carbon brushes tend to wear off with time. So now let's talk about speed control. In universal motors, this is achieved by varying voltage. In such cases, you would have the voltage, the higher the voltage, the higher the speed that you are able to achieve. In which case, you would be increasing the voltage that you apply across the windings of the machine in order to achieve greater speeds. So like if we look at it from this torque speed characteristic, if you were to increase the voltage, you would have a higher torque speed characteristic. And if you use a lower voltage, you would tend to have a lower speed or torque being achieved. And finally, universal motors' main applications are in small appliances, as we mentioned earlier. So things like in home or residential applications, such as you have kitchen blenders, you have fans, and so on and so forth. And also you have portable equipment. So drills, grinders, and so on and so forth. Grinders, and so on and so forth. So that is a brief introduction to universal motors, and we can stop there.